Equation of mathematical physics. And subtitle: Basic types of equations of mathematical physics. Basic types of equations of mathematical physics. The basic equations of mathematical physics, for the case of function of two independent variables, are the following second-order partial differential equations. The first, wave equations. The second derivative with respect to t of the function u equals a squared times the second derivative of u with respect to x. Formula 1. This equation is invoked in the study of processes of transversal vibration of a string, the longitudinal vibrations of rods, electric oscillation in conductors, the torsional oscillation of shaft, gas vibration, and so forth. This equation is the simplest of the case of hyperbolic equation. The second, Fourier equation for third condition. The first derivative of u with respect to t equals a squared times the second derivative of u with respect to x. Equation 2. This equation is invoked in the study of processes of the propagation of heat, the filtration of liquids and gases in a porous medium, for example, the filtration of oil and gas in subterranean sandstones. Some problem in probability theory, etc. This equation is the simplest of the class of parabolic equation. And the third Laplace's equation. The second derivative of u with respect to x plus the second derivative of u with respect to y equals 0. Formula 3. This equation is invoked in the study of problem dealing with electric and magnetic fields, stationary thermal states, problems of hydrodynamics, diffusions, and so on. This equation is the simplest in the class of elliptic equations. In equation 1, 2, and 3, the unknown function u depends on two variables. Also considered are appropriate equations of functions with a larger number of variables. Thus, we waive equation in three independent variables in the form the second derivative of u with respect to t is a squared times the sum, the second derivative of u with respect to x, and the second derivative of u with respect to y. I'm sorry, here this two must be one minute, please. With respect to y. For 1 prime, The third condition equation tree independent variable is of the form du over dt equals a squared times the sum of the second derivative with respect to x and with respect to y. To prime. The Laplace equation in three independent variables has the form the sum of the second derivative with respect to x, y, and z equals 0, 3 prime. Next, subtitle derivation of the equations of oscillations of a string, formulation of the boundary value problem, derivation of equations of electric oscillation in wires. In mathematical physics, a string is understood to be a flexible and elastic reed. The tensions that arise in a string at any instant of time are directed along a tangent to its profile. Let a string of a length L be at the initial instant directed along a segment of the x-axis from 0 to L. Assume that the ends of the string are fixed at the point x is 0 and x is L. If the string is deflected from its original position and then let loose, or if without deflecting the string we impart to its point a certain velocity at the initial time, or if we deflect the string and impart a velocity to its point, then the points of the string will perform certain motions. We say that the string is set into oscillation. The problem is to determine the shape of the string at any instant of time and to determine the law of motion of every point of the string as a function of time. Let us consider small deflections of the points of the string from the initial position. We may suppose that the motion of the points of the string is perpendicular to the x-axis and in a single plane. On this assumption, the process of oscillation of the string is described by a single function u of x t, which yields the amount that a point of the string with abscissa x has moved at time t. Since we consider shell deflections of the string in the xu plane, we shall assume that the length of an element of string m first, m second, is equal to its projection of the x-axis, that is m first, m second equals x second minus x first. We also sum that the tension of the string at all points is the same. We denote it by capital C. Consider an element of the string m prime. Sorry, one minute, please. I cannot see. This x-axis, u-axis, this curve, here L, 0, here we will have m prime. Forces T act the ends of this element along tangent to the string. Here tangent line. This. Angle phi. Here axis x. This. Angle phi plus delta phi. Angle x plus delta x. Oh, abscissa, sorry. Let the tangents form with the x-axis angles phi and phi plus delta phi. Then the projection of the u-axis of force acting on the element m prime will be equal to t times sine of phi plus delta phi minus t times sine of phi. since the angle phi is small, we can put tangent phi approximately equal to sine of phi. It means t times sine of phi plus delta phi minus t times sine of phi will be approximately equal to t times tangent of phi plus delta phi minus t times tangent of phi that equal to t times du of x plus delta x and t over dx minus du of xt over dx. That equal to t times the second derivative of u of x plus beta times delta x and t with respect to x delta x approximately equal to t times the second derivative of u with respect to x, u depend of x and t. Times delta x, where theta lies between 0 and 1. Here we apply the Lagrange theorem to the expression in the square brackets. In order to obtain the equation of motion, we must equate to the force of inertia the external forces applied to the element. Let rho be the linear density of the string. Then the mass of the element of the string will be rho times delta x. The acceleration of the element is the second derivative of u with respect to t twice. Hence, by D'Alembert's principle, we will have rho times delta x times the second derivative of u with respect to t twice equals t times the second derivative of u with respect to x twice times delta x. Cancelling out delta x and denoting t over rho is a squared. We get the equation of motion, the second derivative of u with respect to t twice equals a squared times the second derivative of u with respect to x twice. The equation 1. This is the wave equation. The equation of vibration of a string. Equation y by itself is not sufficient for a complete definition of the motion of a string. The desired function u of xt must also satisfy boundary conditions that indicate what occurs at the ends of the string x is 0 and x is L and initial conditions, which describe the state of the string at the initial time t is 0. The boundary, the initial conditions are referred to collectively is boundary value conditions. For example, as we assume, let the ends of the string at x is 0 and x is L by fixed. Then, for any t, the following equality must hold. U of sorry, 1 minute please. U of 0 t is 0. And u of lt is 0. Two prime and 2 prime. This equation are the boundary conditions for our problem. At t0, the string has a definite shape that which we gave it. Let this shape be defined by a function f of x. We should then have u of x0 equals u in the line t is 0 equals f of x. It is 3 prime. Further, at the initial instant, the velocity at each point of the string must be given. It is defined by the function phi of x. Thus, we should have the derivative of u with respect to t if t is 0 equals phi of x. 3 to prime. The conditions 3 prime and 3 to prime are the initial conditions. For a special case, we may have f of x equals 0 or phi of x equals 0, but if both f of x and phi of x equals 0, then the string will be in a state of rest. Hence, u of xt equals 0. As has already been pointed out, the problem of electric oscillation in wires likewise leads to equation 1. Let us show this to be the case. The electric currents in a wire is characterized by the current flow I of xt and the voltage V of xt. Which are dependent of the coordinate x of the point of the wire and on the time t. Regarding an element of wire delta x, we can write that the voltage drop on the element delta x is equal to V of xt minus V of x plus delta xt approximately equal to minus dv over dx times delta x. This voltage drop consists of the ohmic drop equal to IR delta x and the indicate drop equal to di over dt times L times delta x. Thus, this equals dv. Oh, sorry. Maybe I write down lower. Minus dv over delta dx times delta x equals I times R times delta x plus di over dt times L times delta x. Formula form. where R and L are the resistance and the coefficient of self-induction reckoned per inch length of wire. The minus sign indicates that the current flow is in a direction opposite to the build-up of V. Cancelling out delta x, we get the equation dv over dx plus IR. 1 minute, please. Plus IR plus L times di over dt equals 0. Formula 5. Further, the difference between the current leaving element delta x and entering it during time delta t will be I of xt minus I of x plus delta x and t. Approximately v equal to minus di over dx times delta x times delta t. It is taken up in charging the element. This is equal to c delta x dv over dt delta t. And in leakage through the lateral surface of the wire due to imperfect insulation equal to AV delta X delta T. Here A is the leak coefficient. Equating this expression and cancelling out delta x, delta t, we get the equation di over dx plus c times dv over dt plus a times v equals 0. Formula 6. Equations 5 and 6 are generally called telegraph equations. Telegraph equations. From the system of equation 5 and 6, we can obtain an equation that contains only the desired function I of xt and an equation containing only the desired function v of xt. Differentiate the terms of equation 6 with respect to x and differentiate the terms of 5 with respect to t and multiply them by c. Subtracting, we get the second derivative of I with respect to x twice plus a times the first derivative of v with respect to x minus c times r times the first derivative of I with respect to x minus c times L times the second derivative of I with respect to t twice equals 0. Substituting into the later equation the expression dv over dx from 5, we get the second derivative of I with respect to x plus a times minus ir minus l times the first derivative of I with respect to t minus cr times the first derivative of I with respect to x minus cl times the second derivative of I with respect to t equals 0. Or the second derivative of I with respect to x twice equals CL times the second derivative of I with respect to t twice plus CR plus AL times the first derivative of I with respect to t plus ARI the formula 7. Similarly, we obtain an equation for determining v of xt, the second derivative of v with respect to x equals CL times the second derivative of v with respect to t plus CR plus AL times the first derivative of V with respect to T plus ARV. Formula 8. If we neglect the leakage through the insulation where A is 0 and the resistance where R is 0, then equations 7 and 8 pass into the wave equation. A squared times d2I over dx twice equals d2I over dt twice. And a squared times d2v over dx twice equals d2v over dt twice, where a squared equals 1 over c times L. Okay. The physical condition dictate the formulation of the boundary and initial conditions of the problem. Now I send to you this board in the chat. One minute, please. Now download. Can you see it?
Yes.
Okay.
Yes, teacher.
Very good from them. And next subtitle: solution of the equation of oscillations of a string by the method of separation of variables, the Fourier method. the Fourier method. The method of separation of variables, or the Fourier method, which we shall now discuss, is typical of the solution of many problems of mathematical physics. Let it be required to find the solution of the equation the second derivative of u with respect to t twice equals a squared times the second derivative of u with respect to x twice. The equation first. Which satisfy the boundary value conditions u of 0 t is 0, to u of L t is 0, three. U of x 0 is f of x. 4. And u of du over dt, if t is 0, is phi of x. Five. We shall seek a particular solution not identically equal to 0 of equation 1 that satisfies the boundary condition 2 and 3 in the form of a product of two functions x of x and t of t, of which the former is dependent only on x and the latter only on t. U of xt equals x of x times t of t. Formula 6. Substituting into equation 1, we get x of x times t to prime of t x of x. I'm sorry. Equals a squared times x to prime of x times t of t. And dividing the terms of the equation by a squared xt, we will have t to prime over a squared times t of t equals x to prime over x of x. Formula 7. I'm sorry. The left member of this equation is a function that does not depend on x. The right member is a function that does not depend on t. Equation 7 is possible only when the left and right members are not dependent either on x or on t. that is, are equal to a constant number. We denote it by minus lambda, well, lambda is greater than 0. Later on, we will consider the case lambda less than 0. Thus, T2 prime, over a squared times t of t equals x2 prime over x of x equals minus lambda. From these equations, we get two equations, x2 prime plus lambda times x equals 0, and t2 prime plus lambda times a squared times t equals 0. Formulas 8 and 9 consequently. The general solution of these equations are x of x equals a times cosine of square root of lambda times x plus b times sine of this angle then and t of x t of t equals c times cosine of a square root of lambda times x plus d times sine of a times square root of lambda times times t 11. Where a, b, c, and d are arbitrary constants. Substituting the expression x of x and t of t into 6, we get u of xt is equal to into bracket stay a times cosine of square root of lambda x plus b times sine of square root of lambda x times c times cosine of a square root of lambda t plus d times sine of a times square root of lambda t. Now choose the constant a and b so that the condition 2 and 3 are satisfied. Since t of t don't equal to 0, otherwise we would have u of xt equivalent equal to 0, which contradicts and hypothesis. The function f of x must satisfy the conditions 2 and 3. That is, we must have x of 0 is 0 and x of L is 0. Putting the values x is 0 and x is L into 10, we obtain on the basis of 2 and 3 0 is a times 1 plus b times 0. And 0 equals a times cosine of square root of lambda L plus b times sine of square root of lambda L equals 0. From the first equation we find a is 0. From the second it followed that b times sine of square root of lambda L is 0. From the first equation we find a is 0. It means b cannot equal to 0, since otherwise we would have x is equal to 0 and u is equal to 0, which contradicts the hypothesis. Consequently, we must have sine of square root of lambda times L equals 0. Whence square root of lambda can be only n times pi over L, where n must be natural numbers. It means 1, 2, 3, etc. 12. We do not take the value n is 0, since then we would have x equals 0 and u equals 0. And so we have x equals b times sine of n times pi over L times x. Formula 13. These values of lambda are called eigenvalues of the given boundary value problem. The function x of x corresponding to them are called an eigenfunction. If in place of minus lambda we took the expression lambda is k squared, then equation h would take the form x2 prime minus k squared x equals 0. The general solution of this equation is x is a times e to the power of kx plus b times e to the power of minus kx. A non-zero solution in this form cannot satisfy the boundary condition 2 and 3. Knowing square root of lambda, we can, utilizing 11, write t of t. Equals c times cosine of a n pi over L times t plus d times sine of this angle. Where n is 1, 2, 3, these natural numbers. Formula 14. For each value of n, hence for every lambda, we put the expressions 13 and 14 into 6 and obtain a solution of equation 1 that satisfies the boundary condition 2 and 3. We denote these solutions by UNs of xt. UNs of xt will be equal to sine of n pi over L times x times the bracket in which stay cn's times cosine of a n pi over L times t plus dn's times sine of this angle. Formula 15. For each value of n, we can take the constant c and d and thus write cn's and dn's. The constant b is included in cn's and dn's. Since equation 1 is linear and homogeneous, the sum of the solutions is also a solution, and therefore the function represented by the series u of xt is equal to sum over n from 1 to infinity of UNs of xt or u of xt equals sum over n from 1 to infinity of cn's times cosine of a n pi over L times t plus dn's of times sine of a n pi over L this times n times t times sine of n pi over L times x. Formula 16. will likewise be a solution of the differential equation 1, which will satisfy the boundary condition 2 and 3. Series 16 will obviously be a solution of equation 1 only if the coefficients Cn's and Dn's are such that this series converges and that the series resulting from a double term-by-term differentiation with respect to x and to t converge as well. The solution 16 should also satisfy the initial condition 4 and 5. We shall try to do this by choosing the constant Cn's and Dn's, substituting into 16 t is 0, we get the condition for f of x equals sum over n from 1 to infinity of Cn's times sine of pi n over L times x. Formula 17. If the function f of x is such that the interval from 0 to L, it may be expanded in a Fourier series. The condition 17 will be fulfilled if we put Cn's equals 2 over L times integral from 0 to L of f of x sine of n pi x over L with respect to x. Formula 18. We then differentiate the terms of 16 with respect to t and substitute t is 0. From condition 5 we get equality phi of x equals sum over n from 1 to infinity of dn's times a n pi over L times sine of n pi x over L we define the Fourier coefficient of this series dn's times a n pi over L equals 2 over L integral from 0 to L of phi of x sine of n pi x over L with respect to x, or dn's equals 2 over a n pi times integral from 0 to L of phi of x times sine of n pi x over L with respect to x Formula 19. Thus, we have proved that the series 16, where the coefficients Cn's and Dn's are defined by formulas 18 and 19, if it admits double term-wise differentiation, is a function u of xt, which is the solution of equation 1 and satisfies the boundary and initial condition 2 to 5. Solving the problem and hunt for the wave equation by a different method, we can prove that the series 16 is a solution even when it does not admit term-wise differentiation. In this case, the function f of x must be twice differentiable, and phi of x must be once differentiable. In this moment, I think our lecturing must be ended. Now I give you the picture of our board. Have you any question for me or not? There exist any question? Not?
No.
Not very good. Can you see this board? You see or not? The board that I sent to you in the chat.
Yes.
Okay. It means goodbye, good luck, good weekend for you.
Goodbye. Doctor, can you check me, please?
Who?
Mohammed.
Mohammed. Today we have what? It is
Professor.
2202, yes, Mohammed, or not? Yes.
Da.
Yes. It means I
Hussein
check it. Badvi Abdurrahman, Bitsaid Ramzi Rauf, Janain Ayub, Lua Awad, Mohammed, Adel Jefferson Sabiti, and Atman Tariq Khalifa, right? Or exist another student?
Yes, Hussein Hassam.
Hussein Hassam, okay. I check it you. Goodbye, good luck, good weekend.
Bye.
Bye bye.